Okay, continuing with plate and section forming, we have seen how we go about bending frames, talked about plate bending, and we have seen that if it is a kind of a developable surface, that means with a single curvature like cylinder or cone, some such, the example we saw is the bilge plate of a ship. Right. So there it could be done by passing the plates through rollers, bending rollers, right. 3 roller machines, depending on the upper roller diameter, you achieve the diameter of the cylinder of what you are forming, or the cylindrical bend shape you are going to achieve. For other bending cases, that means where you need to have a, where the surface is a double curvature surface, means where you need to provide for stretching of the plate, need to provide for some kind of strain in the plate. So there also we have mechanism through bending it using a hydraulic press, and another version one can think of is a kind of a universal press. What is this hydraulic press? Hydraulic press is again nothing but, you have a schematically we can see somewhat like this. Say a think some such fixture. This upper portion is the vertical ram, which is hydraulically operated. So if we put a plate here below this and apply force, the plate will bend in a V form, right. When you apply force, the plate will form like this, right. The whole plate somewhat will bend like this. So again the same strategy, you go on feeding the plate, go on turning the plate and apply this force. This is, of course, it has a certain length, right, some such thing. So these are very powerful presses. Like power could be in frame bending, we talked about 500, 700 tons. Here the power can go up to 1000 tons and even more, because here you may need to bend plates which are thick enough, 35 millimeter thick plates, right. So we need again the same thing, you need to achieve the achieve plasticity across the entire thickness of the plate, so that you get a permanent bend shape. You will have to exceed the yield point stress. Anyway, so this is what is a simple bending process using hydraulic press, wherein again you can see, suppose a typical some bent shape is needed to be developed, right. So as we talked about, from this is the patch, we develop the blank, we have the cut plate, and then you have to put it under this press, and again purely a skilled job, means depending on the skill of the operator, who has learned probably from his precedent, right, that how to place the plate, whether, because you see the plate is placed in what orientation, you have to press the plate and keep bending it in stages, right. Again, whether the bend shape is coming to the requirement, again that is checked by, you will have to have those templates already are there for frame bending you have done, and when you produce the blanks, you mark the frame locations. The frame locations are already marked. That marking is also automatically done by in the flame cutting machine, because you see when you have got the definition of the blank, that means the two-dimensional plate that has to be cut, right. That cutting is done in a numerically controlled machine. It may be using oxide steel flame or plasma, that is a material. But if you have automatic working cutting station, it will be a numerical controlled machine. So it knows the boundary, it cuts it, and also you give the information about the frame positions. So it just marks it. So there you can have a different attachment which will mark the frame position. Say this is my frame number 50, 51, 52 and so on, right. Some arbitrarily I have showing. So as you go on bending the plate, you have the templates, you put the template on frame 50 and see whether it is perfectly matching. There is no other way. So thereby the plates are bent to the required shape. So you can see there is a again totally skill dependent, person dependent process and a tedious time consuming process. So these are the areas where one can work and find out to give a solution so that this process can be automated or can be improved, the production efficiency can be improved, right. That is on one way looking at it. Other way looking would be you produce a design wherein you have minimum of curved plates, minimize these operations. That means a design wherein one can have a minimum, but well you will have to, like for example, I can have a section like this. This is also curved, right, or I can have a section like this. This is the difference. That means I give a well-rounded bilge. The moment I give a well-rounded bilge, the forward part becomes double curved, the aft part also becomes double curved, or I can give a chine, double chine. So entire thing remains in the chine construction. So there is no bending of plates involved. The deck, I can give a nice parabolic shape to provide for the necessary camber, or I give a inclined plate with a horizontal plate welded here. So altogether the bending or making curved plates is eliminated. But well, these are one of the examples, but this may not be feasible always, because switching from here to here, this design, I am sacrificing bit of hydrodynamic properties, or I would say I am compromising on the hydrodynamics of it, or in other words compromising in the powering requirement. This may have a higher resistance than this form, right? But as far as smaller crafts are concerned, that difference is negligible, or in other words that doesn't take the predominant role. But you are making a 200-meter long big bulk carrier, you cannot make of chine construction, because there the resistance increase will be very significant. You will have to go for curved plates and proper hydrodynamic shape, so to say, right. So there you cannot avoid. So point is, where we can avoid, let us avoid curved plates, because making curved plates is a tedious job. That is what it is. So that is how this, using so-called hydraulic press, schematically it's like this. The operation is of plate bending, as I have said. So now we say that it being a again all that involvement is there. That means you will have to have templates. So if I make the frame bending in such a fashion, I avoid template, then again it's not done, because for plate bending I need templates. So I improve upon the frame bending process by providing those camera technique and other things. And if I do not produce templates, I mean templates will not be needed for frame bending, but here we see it's needed for plate bending. So what is the other way of avoiding those things. One possible way is making something called universal press, because here you see it's also a universal hydraulic press, I mean a kind of, but here I won't say it universal, I am just naming it hydraulic press because it's only capable of making V kind of bend shapes. Only thing, with my skill I make this V, then turn it, put a stroke here, so I bend this side up and so on and so forth. That's how I get a smooth curvature, right? But I can have a setup which the best would have been if I could have had a concept of male female die, like the ones which are used in case of where you have a mass production of a certain shape. In car, automobile industry, there a lot of plate bending is needed. The entire car body is very nicely aerodynamically designed. How they do it? It's purely by a punch. One single punch, the entire roof is made, the bonnet is made. Means you have specific male female die, right? That means the female die and the male die it punches, right? That means matched die plate bending. There it is feasible because those dies, because you make a pair of die, they will be expensive, very expensive. And why expensive? Because they will be need to be made very strong and heavy and whatnot, because so much of force will be applied. In automobile industry it's feasible. Why? Because you make one pair of die, a mass production. So the cost of that die is very nicely divided in all the thing, but in ship that's not feasible. Secondly, in car, automobile, I am bending what? Probably 1 millimeter thick plates or 0.5 millimeter thick plates. Here we need to bend maybe 35 millimeter thick plate. So imagine the capacity of the die should be. So technically also it becomes somewhat not very feasible, and practically absolutely not feasible, because a pair of, you will need hundreds of such pairs of die for one single ship, which will never be used probably in future. So you cannot do that. So what is the solution? Solution is, one of the solution one can think of, think of an universal die. There the matched die is a one type, but I make a universal die. That means that die can take the required shape, right? That is what I have referred to as universal press. Imagine a situation like this. You have an, say you have an array of such say hydraulic jacks, right? And these all small squares what I am drawing, they are the top of a hydraulic jack, let us think. That means a square array here we have drawn of hydraulic jack, right? So one cross section of jack, if I see, say this is my ground level. So what we have here is, I am drawing it schematically. So imagine a situation that you have a, I mean sufficiently sized array of such jacks, and now this jacks, it has a stroke length, right? So this can be thought of that if you have a plate, say again that same plate, I have to bend it like this. These are my frame lines, right? So I have for this given plate entire x and y coordinates, right? Here also it is fixed, So I know x and y coordinate of each individual jack. So at those x and y coordinate values, I can find out the z values, isn't it, of the plate, of the desired shape. All these jacks can be controlled through a computer, right, wherein the height, operation of the jacks I can control through a computer. So I feed in all that z data, that means the height, for these xy coordinates. So once I actuate, so it comes, say for example like this, in this row, other row in a different, so I get that particular frame line. So that way this flat horizontal surface, from this I can generate any curved surface. Theoretically that is possible, practically also possible, not a very big issue, right. Now similar set of thing can be on top also, hanging from a big framework, right, hanging from a big framework. So I can have a system wherein I have a set of this at the bottom and a similar set at the top. So what in the process we are getting? We are getting that same equivalence of a matched die, isn't it? This is connected to a, say, a framework from which that entire array of this hydraulic jacks are sort of hanging. So the bottom array, I define the surface, right. I generate the required surface. I put the plate on top of it, bring down the top array and press against each other. It is equivalent to that of a matched die concept. In a matched die, what was it? It was somewhat like this. This is my fixed thing and this was my female die, fixed shape. So the plate was kept here and you give a punch, you get that shape. But here this shape is I am generating. So for all different shapes, what it can be easily generated and bent. It can have the necessary power. So that is what is the universal die or universal press. So theoretically and practically both ways it appears to be quite comfortable, quite convincing, quite simple, but unfortunately this is fruitfully it has not yet been used. Why? What do you think could be the well, one aspect is definitely cost, but that is that can be invested. Cost cost is there, but well, it's feasible. It's a one-time investment you do, and the productivity you get out of it is definitely, it will be worthwhile. Plate thickness is a different issue because that talks on the cost. So, well, if I am building, say for example, a shipyard, he will look into this, that one shipyard, it's not like that anything comes in the way you build. You have your vision, you have your plan, you know this is your product range. So if your product range is something say up to say 200-meter long vessels or whatever, you know what are the plate thicknesses you will be handling, what type, etc., and one can think of where it is feasible. It is feasible. So that is not. What is the That means that is also not the major factor which has not made this popular. That is extremely easy. That is not a problem. Not really. What happens is what is the problem is here you see what you will have to do here is, you know, one aspect that whenever we subject a material to a force, a tensile force, say, not work hardening, that what do you call elastic unloading. When I subject it to a tensile loading, what happens? Well, this stress strain I have written, it can be load displacement. Load displacement. By displacement here is elongation. In this case, it is essentially elongation. So, how it will elongate? Let us see. If I go on applying the load, the load will go on in the deflection will go on increasing in a very little fashion. I mean, not heavy deflection. As the load increases, some deflection is there. How much? This much. At this load level, this much of deflection is there. I release the load, it comes back to 0. There is no deflection, no remaining deflection. But our plate bending, I will have to have a remaining deflection. That means a permanent set, as we call it. Permanent deformation is needed. That means I will have to exceed the yield point. Say my yield point is here. And then what happens? It goes somewhat like this. This is my yield point. I need further displacement or more deformation, then the work hardening starts like this, and I stop there. Why I stop there? Because the strain needed is, say, this much. So, if I stop there and release the load, what I will have? My actual bent shape will remain. That means the available final strain will be this much, residual strain will be this much, less by this much. Under load it was so much, the deformation. That means when it is under pressure from both the top and bottom area of hydraulic jacks, it will perfectly conform to the plate shape, required shape. But the moment I release the load, it will straighten out, so called it will spring back, right. So, this is my extent of spring back. Which very easily can be seen in a simple experiment of this, or even you take a small steel bar, you hold it in a hand, you bend it and release it, you will find it is straightening out little bit, because this elastic unloading will be always there. This is my elastic unloading, that is what is called. That means steel has this property of elastic unloading. Had it been lead, it does not have that elastic unloading, because it is fully plastic material sort of. There is no elasticity in it. Lead is a soft metal, it does not have any elasticity. You bend it, it remains in that state. You give any shape, it is like plasticine, the kids they play, right. But steel is elastic material, so it will have this spring back effect. So, that is the main problem. So, one can, so what is the solution? Solution is one will have to assess how much spring back may take place. So, accordingly you bend it further such that after releasing of load, it will come back to the, it will spring back and come to the required shape, desired shape. That is theoretically feasible. Now, what are the practical difficulties doing that? No, it's not that way, because as it is the same plate, if I bend in a normal hydraulic press, I am bending it. That is not the problem. Problem is assessing of this, how much spring back will take place. That is the problem. Why? Because how much spring back action would be there, that is a function of what? It is a function of all those mechanical properties, essentially function of your, well, sigma y, function of modulus, right? Primarily these two. Right? And then other things, the dimension of the plate, thickness, etc. But material properties, these two, primarily these two. It will depend on that. Now, let us see what is the value of this sigma y as far as normal strength steel is concerned. What is the value for normal strength steel? That means we are not talking about high tensile steels or high yielding steels, just say normal strength steel, because probably around 80 to 90% of the steel used is normal strength steel in shipbuilding industry. The sigma y yield stress is of the order of, yeah, it will vary within this zone, 220 to around 240 newtons per millimeter square, or I think so many megapascal, isn't it? So that is what. Similarly, E is of the order of 210, say, gigapascal, right? This is megapascal, that is gigapascal, right, of that order. Now, you see, now which value to take, 220 or 240? That is the problem. Which value to take? If I take average 230, well, so any value you take, your spring back will be different, and that difference could be of the order of several millimeters, and several millimeter difference I cannot tolerate, because say my plate thickness is 8 millimeter, I am making a frigate, side shell thickness, say part of the shear strake at the forward part is say 12 millimeter only, and there this kind of variation gives me a variation of 6 millimeter in the bend shape, half the metal thickness. I cannot weld, the next component will not match. The tolerance level is hardly plus minus 1 millimeter. So that goes grossly out, right? That is the problem. So which value to take? That creates a problem. Also, now you have the steel plate. Now, if I want to find out the material property, suppose I take a sample here, I test it, it will give me some yield stress, say 228 gigapascal. I take a sample here, it may be 239. I take something here, it may be again something else, but all will fall within this range. So that is what it is. That means the material property, this steel material is not a so called a material of unique property. I mean, is not made of single crystal that anywhere only one single physical property will be there. No, steels are qualified to a category of steel depending on whether it is falling within that prescribed zone. This is the prescribed zone for normal strength steel, right? But the zone is wide enough to get my spring back value also wide enough. So then becomes the problem. So what is the solution to this? All problems should have a solution. Maybe not feasible today, but tomorrow. So what is the solution? Solution is simple, right? Like when we had been using that conventional hydraulic press, what that skilled operator was doing, he was bending it checking with a template, and he will find it has to be bent more. So, he is again bending it at different location, again checking with template, and at one point he may find that it has been bent excessively, it has to be straightened. Reverse the plate, he applies sufficient enough load to straighten it out. That means, by trial and error, every stage he is checking and he is either bending it or straightening it, getting the final shape. Same thing we can do here also. That means, we will have to have a mechanism of monitoring the shape what we are getting. Like in case of frame bending, we have talked about monitoring using a camera, right, and bending it and checking it with the prescribed bend form. So, same thing is also feasible here. If we can have a mechanism of sort of monitoring the curved shape, this shape what it is generating. First, I generate the surface as required with preliminary calculation of this spring back, because well, some value we take, probably take the mid average value. With that spring back, I add that springing back allowance to the curved surface, to the defined surface, right, and accordingly actuate my jacks, press it down, it bends, release it, and then this surface has to be checked for the coordinates, whether it has come correct or not. So, again that same problem, how do you check it? And now it is a surface, it is not only one line. In case of frame, it was just that edge, it was a much easier thing. Now, the entire surface has to be checked. That means, essentially how do you check a surface? We will have to make a grid on the surface probably, right, and that these coordinates are to be measured and checked with the my required surface. Those coordinates are there, so I will have to check. So, how do we do this? That means, here we need, it cannot be just take a camera image and do, can be done, but that will be tremendously computationally expensive and time consuming probably, because if you take a camera picture and eliminate all and extract this coordinate data could be difficult. Instead, a laser beam scanning can be is possible, and in a pre-programmed way it scans and takes only the z coordinates at predefined points, because what you need is xy coordinates are well fixed, only the variation is z coordinate I will measure. So, by means of a laser scanning, one can get this data. So, that data, with that data you generate the surface, match with the required surface and find out whether it is to be in some place further bent or straightened. Accordingly generate the surface, accordingly actuate the jacks and give the second punch, third punch, fourth punch, and finally it comes out. So, here the problem becomes that saying that a laser will scan and will take the data, generate the surface, match and do possible, but still practically not that yet feasible most probably. There could be problem of computational requirement, could be problem of cost involvement, could be problem of volume of work, all taken together it has not come out. Means people have tried full scale prototype, but has not been is not finally utilized commercially, because other aspect is also there, the all this will have a cost component to it. Now, we will have to see also what is the volume required, because you can see when we are talking about like in some vessel, by doing this I am eliminating this, and when we are talking about there is a definite hydrodynamic requirement, and where I cannot do away with your curved shapes, that means big vessels, and big vessels what we see, only these two parts will have double curvature plates. What I have drawn is fairly proportionate. So, you can see probably 2/3 or more than 2/3 does not need curved plates. Whatever it needs is in the bilge. For that you do not need such complicated things. Simple rolling machine will do it immediately. That is done very fast. Right. So, only little amount of curved plates in the forward and in the aft. So, if it takes longer time for produce, let it take, you plan it accordingly. When the work on this part is going on, preparation of curved plates can start. By the time the work is over here, the curved plates are ready, you get on with the forward block and the aft block. I mean, all those planning can be done. So, for that you do not need a high productivity machine, that is also there. So, all these are to be seen, but the difficulty what remains is, it is not productivity, difficulty remains is on the availability of skilled worker. That is becoming difficult to operate this machine, that availability of skilled worker, because in a shipyard you will have few. So, in one shift, say 2 persons are coming who are doing this job, if he falls sick, the work stops altogether. It is that kind of skill, right? That is the problem. So, there are many aspects when you develop a technology. Developing is something, concept development is something, from that prototyping is something else, and finally implementation is altogether something else. There are many factors they come in which will dictate whether the technology is to be developed, if developed, whether it can be implemented or not, right. So, that is what is the universal press. So, here we see universal press is feasible. The whole process of plate bending can be more or less automated, because all these operations will go automatically. Laser will scan, computer will compute, it will direct how much is to be actuated, the jacks, feeding of the plates is through roller. So, one man will be operating the whole show. So, it is fairly automated and efficient process could be. But well, these are the drawbacks. So, what happens? Primary drawback is springing back action. Primary is because of the material is elastic, and it has a, when it is unloaded, it will spring back. To evaluate that exact how much it is springing back, there comes the problem. That means at one stroke you are not sure that you will achieve the required shape. So, you will have to have a monitoring system. Monitoring system becomes a complicated issue. That is all. So, that is what all about the your mechanical means of bending. Now comes the thermal means. What is the difference? Difference is, in both the cases, what we did is we applied a force, generated a bending moment, thereby we exceeded the yield stress, right, and depending on the orientation, direction and all that of bending moment, I got a bent shape, both for plate as well as for frames. In case of thermal, it is essentially a thermal load, which leads to deformation. That means formation of, well, I may mention as thermal strain. Where from I am getting thermal strain? That means I am getting some bending moment is forming, definitely. Which is giving rise to the strain. Since the bending moment is from thermal load, so I am getting a thermal strain. Well, so how it happens? Let us first see how that thermal load comes into play, and then we will see how that can be applied. So, if we do a small experiment, because we know if we heat a metal piece, it expands because of some property called something called coefficient of thermal expansion, some property it has. Depending on that, depending on the extent of heating you are doing, you will have a expansion of the material, and upon cooling it will come back to the original shape, right. So, there are two cases. Say I have a small say iron block, a steel block on a table, and the same steel block I am putting on a against a vise. You know vise, in workshop we have. So, what I am doing in the vise is not actually pressing it hard, but just holding it. By saying just holding it means I have tightened it enough so that some friction it is holding, it is not falling off. I am not applying any great force as such, little force, so as to have overcome the weight. The frictional force is enough to overcome the weight of that small cube. So, these are the two cases, and this, let us assume we heat it with some heat source. Let that heat source be a, say, a gas flame, right. Same thing also I do it here. I just heat it, right, heat it to a certain temperature and leave it. So, what I will observe in these two cases? In this case, what we won't observe anything as such in naked eyes. It will be just heated up and left. If I touch it, I will feel it is very hot. But in this case, what I will find is after I have left it, it will fall down. It was lying there, now it will just drop on the ground. By that means it will be lying on the ground, basically. It will fall off. Why it is falling off? Obviously, I am assuming that because of this heat, these clamps have not changed any of its physical property or anything. That means something has got changed in this cube. Now, if you measure the cube, both these cubes which has undergone equivalent heating, we will find that this cube retained its original shape, original size rather, retained its original size. Here I will find the size has changed. Yeah, this has decreased. So, what has happened is essentially, say, one cross section I am drawing only, the front elevation which is seeing, it may have become, or it has become like this. This dotted line is the changed shape. Obviously, I am drawing little exaggerated. This means in the breadth, as if it has shrunk, and now there should be conservation of volume. So, it has increased in this. That has happened, whereas it has not happened here. So, that means this vise had some role to play. What role it played? When I heated it, it tried to expand, isn't it? It tried to expand in this direction, but since the clamp was there, it could not expand. So, a reverse compressive force was generated. That means because of the clamp, a compressive force was generated. I can call it a compressive stress, right, that worked on the plate, right. And then when I withdrew the heat, the cooling started. So, in the phase of cooling, what was happening? It tried to expand, it could not expand, but it was free to contract. So, it started contracting. That contraction process was assisted by these compressive stresses which formed. So, it is freely contracting, plus additional assistance from the thermal compressive stress is developed, plus the temperature is high. So, I know the stress temperature distribution. Yield stress is a function of temperature. As the temperature is, this is my yield stress as room temperature, say this is my 30 degrees centigrade. It drops like this, it becomes 0 where? Yield stress, melting temperature. When the metal is liquid, obviously it cannot take any stress, it flows, isn't it? Here the material was flowing because of plasticity. The metal was flowing because of plasticity, but this value is very small. If the metal is totally in liquid state, it flows without any stress. It takes the shape of the wherever you keep. So, in this case what is happening? The temperature is somewhat at the higher level because I have heated it up. When it is cooling down, still from a high temperature it is coming down slowly. So, the temperature was here, then my yield stress was less. Gradually, well, cooling down, so temperature is coming down, yield stress is gradually increasing, but it is always less than the normal yield stress, right. So, the forces which are acting, the compressive forces as well as natural contraction, they are taking place more comfortably, I can say, because at now I need a lesser load to deform it. Like a blacksmith, what he does, he hits up a metal piece and he just very casually he hammers, not with full force, and that thing takes shape. Means what? He works at this, somewhere at this stress level, he is working at this temperature level, it is red hot, 800 degrees centigrade say. He is just small heating, means he does not need much stress to be developed because the yield stress has lowered. So, that is what is happening. So, thereby it shrinks. So, this is the basically the mechanism of deformation. So, this how it works in a in actual plate bending or frame bending case, that we will see. Oh yeah, we still have some time, sorry. Anyway, or maybe you have a class after this, right? Okay, let us complete here today.